Okay, today I'd like to derive a pretty interesting result about the slopes of tangents and secants of a parabola. We'll need this for a future problem, and it's actually a pretty useful geometrical idea that comes up kind of frequently or makes a lot of problems easier with these parabola stuff, which of course projectile motion is all about. So let's imagine I have a parabola. And yes, I am basically thinking of this as some sort of projectile motion trajectory, but let's do this geometrically, a parabola in space. It does not have to be concave down, it could be concave up. I'll just draw it the way we'd expect a trajectory to be for projectile motion. Let's imagine we take 2 points on that parabola, I'll call them A and B, and we will draw the chord AB. So this is part of a secant line that cuts through the parabola in 2 places. Let's also construct the 2 tangents to the parabola at points A and B. So we have these 2 different tangents. They go off, they will meet somewhere. If you go out to infinity, maybe the tangents would be vertical, but aside from infinity, there will be an intersection point of those 2 tangents. And my goal is to try to relate a few angles here. Let's call this whole angle theta. So that angle is theta. That is basically, actually let's call it theta naught. Okay, that is our launch angle. That's the angle with the horizontal. I've drawn in some dotted horizontal and vertical lines here. So imagine we have this horizontal, we have an angle of launch. Theta naught is the angle of the tangent at that launch point. And I will also go ahead and draw in another horizontal here, and I will call this angle over here theta. Notice that the way I've drawn it, theta is actually negative here. It points downwards. That's okay, but I want to keep this general in case B ends up being on the same side of the parabola or of the vertex as A, in which case both of them would be positive. So this is generic. Let's draw one more angle in, and that angle is this one, which is, you might call it the angle of elevation of point B with respect to point A. In other words, if you were standing at point A and you looked straight towards point B, not along a curve, but a straight line, this angle would be the angle of elevation between the horizontal and that line of sight. And I want a relation between these 3 angles. That's my goal. Now, there are plenty of ways of doing this sort of calculus-wise or algebra-wise, but let's try to do this geometrically. We're going to use a fact, and I won't prove this fact. This was known in antiquity to Euclid before Archimedes, a fact about parabolas, which is the following. If I draw a line that passes through the point of intersection of 2 tangents to a parabola and is parallel to the axis of symmetry of the parabola. So notice I've drawn this so that the axis of symmetry is vertical. It's maybe, say, here. Notice the axis of symmetry does not pass through that point. But if I draw a vertical line, which is parallel to the axis of symmetry, it is known and can be proven with no calculus or anything, this is 2,500 or 3,000 years ago, that this divides this chord into equal segments. In other words, it will pass through the midpoint of the chord connecting those 2 points of tangencies. Wow, amazing fact. Not really taught in like high school geometry, but it's true. You can kind of see a similar theorem from circle geometry, right? If you draw, this is a little more general, but if I did have a radius drawn from some circle's center, you know that it bisects a chord if and only if it's perpendicular to that chord. There's something similar going on here, except we don't have perpendicularities. We have a parallel axis to the axis of the parabola. Okay, so using this fact, and this fact alone, I now want to figure out how these angles are related. All right, well, we have a little bit of a trapezoid here. Notice that this line here has now been bisected. We have these 2 vertical lines here and this horizontal line here. And actually, let me draw this horizontal line so it actually passes through the point of interest here. So I'm going to construct this horizontal which passes through this intersection point. I now have this trapezoid. I'll call it ABCD. Okay, it's clearly a trapezoid because the 2 lines are parallel, but AB is not horizontal. although it could be, it works there too. Well, if that's the case, then we know that this red line is actually forms a median of this trapezoid, which means these two will also be divided in two. So maybe I'll call this point E. And we have that DE and EC are congruent. Now what I'd like to do is calculate the slopes of these three green lines. So let's calculate the slope of segment AE. So that's this segment here. Well, it's going to be rise over run, if you want to call it that. The rise from here to here is just length AD, and the run is just length DE. Okay, so there's the slope of my first tangent at point A. Let's also calculate the slope of, say, EB. This is this segment that forms the second tangent on the other side. Now, notice the way I've drawn it, this will be a negative slope. It doesn't have to be in general. If B, again, was over here, this would also have a positive slope, but I do have to be careful if I'm talking about lengths to include an extra negative sign. So I know that the rise here is actually a fall. It's CB. And the run is EC. All of these are now positive lengths. I had to include the negative by hand. Finally, we have the slope of AB, the chord, or the slope of the secant. The rise is this distance. Maybe I will give this a letter right now. Point F. So the rise is going to be BF, and the run is going to be AF, which is actually equal to DC. Now, because of the congruencies here and here, a lot of these can actually be split up or simplified. So I'm going to write this. BF is the same thing as CF minus CB. Okay, that's just this difference between the full height and the height up here. And AF, which is the same as CD, well, I'll just write that as CD for now. Now we can split this into two fractions, CF over CD. Well, let's think about that. CF, that's this whole distance. I'm going to call it AD, which it is, because I want to connect it to the slope of segment AE. So in the first term, I'll have AD over CD. Okay, CD is just twice DE, because CD is DE plus EC, and EC E is the midpoint of that. Then for the second term, which I'm splitting off, I have CB, I'll leave that, divided by CD, but this time I'm going to write CD as twice EC. Okay, again, I'm using the fact that this is a midpoint. And now it's written in a very nice way. I can factor out the 1/2, which comes from each of those terms. AD over DE is just the slope of AE, and negative CB over EC is just the slope of EB. And that really is the result we want to prove. I'll write it in tangents in just a second, but this is an interesting property. It tells us the slope of a secant, or the slope of a chord, of a parabola, is the average of the slopes of the two tangents at the ends of the chord. That's interesting. I think that's pretty cool. Okay, now we can rewrite everything in terms of tangents, because obviously the slope of this line is just opposite over adjacent, but that is tangent, right? It's rise over run. It's a tangent of phi. So tan phi will be equal to 1/2. Well, the slope AE is just going to be the tangent of this angle, theta naught. And EB is going to be the tangent of this angle. Now, at this point, maybe you're worrying a little bit about the negativity here. I'm letting this theta be positive or negative. It doesn't matter. So I really am going to leave it as a plus, tan theta. We just have to understand that theta needs to be measured appropriately from the horizontal as either positive if it's counterclockwise or negative if it's clockwise. So again, said a different way, trigonometrically, the tangent of the angle of elevation is the average of the slopes or tangents of the two tangent lines to the parabola at either end of that chord. All right, so this is the result we wanted to show, and we'll use it in a future video, QED.